Another concept that's going to show up a couple times within this section is rather than treating y as though it's a function of x, we may be treating x as a function of y. Now, whatever pertains to a function, when x is a function of y, things tend to get reversed. Instead of things like the vertical line test, this will pass the horizontal line test. So imagine for a moment that we have a Cartesian plane. This might be x as a function of y. X is a function of y because it passes the horizontal line test rather than the vertical line test. Additionally, we might see another function of y, like x equals g of y. Now, when y was a function of x, we were looking for a top function and a bottom function due to the fact that that was a larger y value and a smaller y value. For x as a function of y, we are going to be looking from left to right. That is, a larger x value versus a smaller x value. Assuming that we also have an interval associated with this, we'll call that the interval from c to d. Then the area between these two curves would look like the following. To set this up, we would, once again, break the interval from c to d up into a bunch of little tiny subintervals, but ultimately, what you're going to be looking for is your right function, the larger x value, versus the left function, which is the smaller x value. The area in between these curves will be denoted as the definite integral from c to d of the right function minus the left function dy, no longer dx, and it is important to make the distinction between those. Now, with those things in mind, let's go ahead and take a look at the following example. Here is x as a parabolic function of y. And here is another. I'm told that this is x equals y squared minus 4. We would expect a positive coefficient here because it opens in the positive x direction. And for this other one, we have x as 2y minus y squared. I've also been informed that this is negative 3, 3, and that this other point of intersection is right at the origin, despite how I drew it. The area in question would be this area right here. What we're going to do is use calculus to find this area. Now, within this interval, we are going from left to right with our sample rectangle. So that'll look something like this. So to get the length of this rectangle, we're now going left to right. So the right function is going to be this function. This function is actually the parabola opening to the left. So that'll be 2y minus y squared. The left function is going to be the other function, the parabola opening to the right. That is y squared minus 4y. As far as bounds for this are concerned, we would be looking for y values, not x values. The lower bound for the interval is the intersection at 0, 0. We'll be taking the y value of 0. For the upper bound, we'll be taking the upper bound to be the y value at that point of intersection. That'll be 3. If those were not provided for us, we could set these two functions equal to each other and solve for y. So the total area in question is going to be equal to the definite integral from 0 to 3 of the right function minus the left function, dy. This can be integrated using the power rule, but before I use the power rule, I'd like to simplify algebraically. 2y minus negative 4y will be 6y, and negative y squared minus y squared will be negative y squared. We integrate each term according to the power rule. We'll get 3y squared minus 1/3 y cubed, going from y equals 0 to y equals 3. Plugging in y equals 3, we'll get 3 times 3 squared minus 1/3 of 3 cubed, minus 3 times 0 squared minus 1/3 of 0 cubed. That is a lot of 0. Simplifying what's inside this set of parentheses, I see 27 minus 9. Final answer for this one, 18.